before I get started, opening it up to online as well as you here in person, how much do you remember about quadratic equations? Like the x squared, parabolas, zeros?
I can get through it when it comes back up in school, but I don't remember too much of it,
Okay.
like off the top of my head.
And then on the flip side, how do you feel about matrices?
I can do matrices.
All right, I was just debating on which of those two topics, those are the two ones that we're gonna cover today, and I was wondering which one to start with or give more time to.
Either way, I think.
All right. We'll go ahead and start with the quadratics then. All right. I'm looking at a sea of blank screens and muted microphones, so I'm assuming people are there. But my name is Aubrey. I am a,
I found your phone.
Oh.
At the corner there.
I set it down when we were doing tables. So, my name is Aubrey. I am actually a math teacher and tutor, and I took the ACT when I was in 8th grade, got a 25, didn't know what that meant. Took it again when I was a junior, got a 32, did wonderfully well except for the English portion, and so had a really wonderful advanced composition English teacher, and finally started figuring out what they wanted with that, and took it again, got a 32 again. English score went whoop, math score went whoop, because I forgot my calculator, day of test. And so I took it cold and was obviously a little bit slower and didn't get finished. But by then I thought, I get into college, life is good, I'm done, and moved on with my life. But part of me has always been curious, should I try it again? And the answer is no, but you guys can do better than me. So, whatever you want out of this, please feel free to ask questions. So, we're gonna go ahead. I noticed that on his previous recordings he says 5 minutes, and then he doesn't give you 5 minutes. So we're going to pretend that I'm giving you 5 minutes, but in reality it's probably close to 2 or 3. But go ahead and start on page 8 of the book. We're going to be working with quadratic equations, and then about halfway through we're going to switch over to matrices. started before I dive into my idea of what you think you should learn. Any questions about that, or what on earth is this? Okay, so very short review. A monomial, mono meaning one, is any term. It can have any numbers at once. It can have as many variables as it wants, but it's only stuck together with multiplication. And so it could be 2, or 1/3, or 583. Any number at once, but there is number, and it's going to be stuck together with as many variables as you want to any degree. It can be to x, y, z. It could be h to the 4th. It could be x to the 3rd, z squared. But all of these numbers and variables are stuck together only with multiplication. The instant we add or subtract other monomials, it becomes a polynomial, meaning poly, many. And so we can have our 1/2 x squared, and then we can add in 4z, and we can add in 8y plus b. Very ugly polynomial, probably pretty useless, but it is a polynomial. And each one of these pieces is a monomial. Very specifically, there is one operation that has been left out. We have multiplied, we have added. I can change any one of these to subtraction, and it still works. The instant you divide by variable, it goes away from being a polynomial and gets into a rational function, which will have very different behavior. So in order to be a polynomial, variables stuck together with multiplication, added or subtracted together, no dividing by variables. That gets us into a different type of equation, and we're not dealing with those right now. So for today, we're dealing with quadratics. And I honestly don't know where quadratic comes from. Probably squared, because if you multiply something, it makes a square. And so quadratic equations are going to have their highest degree be x squared. We don't have x to the 3rd, we don't have other variables. There's only going to be one variable, and it's going to be the highest degree that it's squared. It could be x. We could have f of x equals x squared. They're very fond of h of t because this one is frequently used for height and time. Shows up in quadratics a lot because gravity acts like a quadratic function. But no matter what happens, whether it's this monomial basic x squared, or we have a polynomial with lots of different things, there's still only one variable, and that variable's highest degree is being raised to the 2nd power, or being squared. What this means is that quadratic equations are going to have this shape. It's called a parabola. And the answers or solutions of these are frequently found what variable makes this answer 0. And so solutions are also called zeros. It can happen that it just touches that zero line once. It can happen that it crosses our zero line twice with two solutions. Or it can happen that it never reaches that zero line at all. No solution. And so it's possible to have up to two. It's possible to have only one. And this one, they come out being called imaginary. And that's where you get those square roots of negative numbers. But it's either two solutions or less. All right. Questions over any of this stuff? This is background, but still good. Okay. So, when you were working with these in algebra, you first introduced to these in Algebra 1, and then they show up again in Algebra 2. You learn to find these zeros or roots by two main ways. One of them is factoring, the other one is the quadratic equation. Completing the square is in there, but it's more of a mental exercise explanation. Completing the square is why the quadratic formula exists. Quadratic formula comes from completing the square for any case. But the general form for quadratic equations is ax squared plus bx plus c. A, B, and C are just the stand-in representing any number that is in front of an x squared term, an x term, the number all by itself. In this case, very simple. A is 1, because there's 1 x squared. B is 0, there's no x terms. C is 0, there's no number terms. This one, a little bit easier to see. A is 2, B, -3, C is 5. And so that's where those pieces are coming from. I don't know if they give you the quadratic equation on the ACT. I don't think that they do. And so if you have not memorized it yet, find a way to. There are people who sing it to the tune of Pop Goes the Weasel. I am not one of them. So before we get to the whole equation in the book, I'm going to jump down to the part where it talks about the discriminant. The discriminant is negative b squared minus 4ac. And this part right here tells us what's going on with those roots. If it turns out to be a positive number, we're going to have those two roots. If it turns out to be 0, we're going to have that one touching root or double root. If it turns out to be a negative number, that's where these imaginary things come in. Because in the total equation, it says negative b plus or minus the square root of this discriminant, negative b squared minus 4ac, all over 2a. And so in the greater scheme of things, you can see what's going on here. If you have a positive number, you take this, and this plus or minus gives a wobble, and you have two answers. If it's 0, plus or minus 0 doesn't change anything. And so you end up with a single double answer. And if it's negative, square root of a negative number gives us imaginary number, imaginary roots. Alright. Time-wise, we're doing alright. Questions from the online crowd? Like talking to ghosts. So, with these, there are some shortcuts or mental patterns that you can find that can help you understand what's going on with these equations, and so I wanted to talk about those. So I'm just going to have f of x equals negative 3x squared plus 8. Sorry, trying to run out of room there at the end. So, one of the first things to know about these equations is direction. If you notice, the very first number is known as the a, and that leading coefficient is telling you how this graph is going to behave. And so here we have a negative 3, a positive 4, a positive 1/2. So the very first thing to know is that sign tells you what direction it goes. And the best memory device I have for it is, if it's positive, it smiles. If it's negative, it frowns. If this is a negative number, it's going to be opening downward. It's going to be upside down, flipped, however you see that. If it's a positive number, it's opening up. And this one, also opening up. And so if it's negative, it's frowning. If it's positive, it's smiling. And that's the best way to remember it for me. If you've got a different method, go for it. The other thing is that this number out front here is telling you how wide or skinny the graph will be. The very basic x squared function starts at 0, 0, goes up 1 over 1, back 1 over 1, and then 2, it'll go up to 4, because 2 squared is 4, negative 2 squared is also 4, and so it'll open like that. If we multiply that by 4, it's going to go up 4 times as fast. Where this was 1, it's already at 4. Where this is 4, it's off at 16. Multiplying by 4 makes it grow incredibly rapidly. The same way 3, it's going to be flipped upside down, but it will still be dropping 3 times as fast as that. But if we put this 1/2 out in front, it will slow it down. Now it's still going to be positive, but rather than going 1, 1, it'll only go 1 over 1/2, 2, 2. And so it ends up being a more gradual shape by putting that 1/2 in front of it. And so even without knowing anything about those equations, I can tell you those directions and what speed they will be changing. So now, last question is max or min? They're going to ask you, is this equation have a maximum or a minimum? And they're talking about what's known as the vertex, which is this point in the graph. So, this one, negative, frowning, opening down, however you see that, is that a max or a min?
Maximum.
Yeah. And that's really hard for people to get their brain wrapped around, the idea of it's negative, it has a maximum. Because you think negative, minimum, low, but no. This is the best it gets, and then it drops back down. Here, positive, opening up, smiling, however you see it, has a minimum. This is the lowest it goes, and then it goes back. The lowest it goes, and then it goes back. And so distancing negatives have this maximum, positives have a minimum, is a really hard mental connection for people. And so if you just need to say, oh, positive, oh, minimum, 2 seconds to give yourself a sketch rather than trying to process it through in your brain of, just draw it out. Alright, so whether you do the discriminant as a separate step or not, that one's really up to you. Most people do not, just because the discriminant is part of the quadratic equation. And so it's really easy if we look at this one. We have negative b is 4 plus or minus the square root b squared, 4 squared. I say 4 and I write b. Minus 4 times a times c all over 2a. And so that is setting up the quadratic equation. But looking at just this part in here, 4 squared is 16, minus 4 times 4 is 16 times 1. 16 minus 16 is 0. And so this one is going to have that double root answer. It works out to negative 4 over 2 times 4 is 8, negative 4 over 8, negative 1/2. And so on our graph, if this is 1, it's going to have that double root at negative 1/2. So So, if the discriminant's not 0, for instance with this one, we're going to have negative 8 plus or minus square root of 8 squared minus 4 times negative 3 times negative 3 negative 3 times negative 3 is 9 times 4 is 36. 64 minus 36, that would be a time to pull out a calculator, but it'll come out to be positive. The important thing to notice is that in the equation there's also this front half, and so the quadratic equation, if you can memorize it, has all the information that we're looking for going on at the same time. It's got this discriminant that tells us about the roots, And this part right here tells us the axis of symmetry. It tells us that middle. And so if you can memorize the whole equation, you have got like a 3-for-1 deal. You've got this equation, you've got the discriminant, and you've got the axis of symmetry all together. And so axis of symmetry tells you where that center line is. If you've got the axis of symmetry, do you have the x value or the y value? Yeah, it's the x value of here. And so to find the y value, to find this vertex, you just have to take your x value, plug it back into the equation, and find, okay, what is the y value? For this one, it came out to being the same thing as our zeros, but this -4/8 came out to -1/2. If we put 1/2 in here, sorry, -1/2 in here, it would come out to 0. And our vertex is at -1/2, 0. Am I throwing too much at you yet? Okay.
No,
All coming back to you now?
slowly.
So, the last thing that wasn't in this book, but I think it's important to talk about right here, what do you guys remember about domain and range?
Is X, range is Y.
Domain is all the values of x that work. Range is all the values of y that work. For a polynomial, the domain is going to be all the x's. When you get into dividing by a variable, you can start having, nope, that doesn't work because I have a divide by 0 error. But for polynomials, range is typically going to be all real numbers for the x's. But for the y's, for instance, this one right here, does it ever get below that x-axis? No, because it comes along and it goes, nope, turns around. So for this, the range, you would find that vertex and say, range is y is greater than or equal to 0. And it's everything above that. Here, where did our upside down one go? So it would be everything below that vertex. The range is all the numbers below that vertex, because other than that, doesn't have any numbers up here. All right. So, moving on to the next page, and what did I do with that eraser? I'm adding 1,000. Wow. I have it. I did. Oh, there it is. So, factoring, it's kind of a gamble. Quadratic equation will always work, but factoring, if it does factor, is a lot faster. And so if it happens to factor, great. If it doesn't, you have to go back and do the quadratic equation anyway. And so, the example they give is x squared minus 7x plus 12. This is going back to FOIL, the first outside, inside, last. This number ends up being the sum of your two numbers that aren't x, and this one comes from the product of our two numbers that aren't x. And so we're trying to get back to a binomial, two pieces, and it will have x and x. So there are 4 scenarios with this. We're gonna have x squared, and we're gonna have plus x squared plus minus x squared minus plus, and x squared minus minus. So, since this last number comes from a product, how do you get a product that's positive? What can you say about the signs of your 2 numbers that you start with?
Both positive or both negative.
Yeah, they're both positive or they're both negative. In order to get this where they're positive, they're going to be same sign. In order to add up to a positive number, they would have to be positive. In order to add up to a negative number, they're both negative. If we have a negative number for our product, you got one of each. One negative, one positive. So, I'm going to abbreviate to diff. If they're a different sign, but they add up to a positive, I'm going to say big positive. If they add up to if they're a different sign and they add up to a negative, it was more negative or big negative. And so this is the background work of factoring. From there, it's a matter of finding the numbers that work. On this one, our product is 12. 12 is positive. So they're going to be the same sign. They have to add up to the middle number. Middle number is negative. So they're going to be the same sign, and they're both negative. So finally, we need factors of 12 that add up to negative 7. So for 12, we could have 1 and 12, 2 and 6, 3 and 4. And in this case, they're all negative. Which ones add up to negative 7? 3 and 4. So we have x minus 3, x minus 4. Final tricky thing. If they ask you for the zeros, and this is the factored form, what are my zeros? Positive 3, positive 4. Non-negative 3, negative 4. Zeros are what makes this 0. If we have 3 minus 3, it makes it 0, so our 0 is 3. 4 minus 4 makes it 0, our 0 is 4. And so the final thing for factoring is, remember, you need what makes it 0, not just, hey, I factored and look, their number is, because it's the ACT. They think and they know exactly how people will mess up, and they offer you that answer. All right. So that one is quadratics. So go ahead and flip over to page 12. And on this one, I'm giving you time to read over it purely for the selfish reason, so I can set up a board and not waste your time. So, of all, matrices made up of rows and columns. They were a mathematical interest, but came into their own as far as being indispensable with the advent of modern computing. It's a way to organize a lot of information, and computers, because they're methodical and can just run through a program over and over again, they aren't intimidated by a matrix that happens to be 100 rows and 200 columns. It can just munch the numbers and go through it. So it is useful, but honestly at the high school level it's kind of the introduced training wheels thing, and so a lot of times it feels like, why are we doing this? But it does get used in the real world. So first of all, how do you list the dimensions of a matrix? Rows by columns. So we're going to do the rows first and the columns second. So this one would be 2 rows by 3 columns. This is a 2 by 3 matrix. This one, same thing, 2 rows, 3 columns, 2 by 3. This one, 3 rows, 2 columns, 3 by 2. This one, 2 rows, 2 columns, 2 by 2. So, the other thing is, how do you find information inside of a matrix? So if I ask you for the value of C21, what does it equal? Almost. So again, remember rows and then columns, row and then column. So this one says row 2, column 1, C, row 2, column 1, value is 1. And so just knowing how to pick numbers out of the matrix can be helpful. So the first thing that you can do with these matrices is to add or subtract them. Which ones of these can we add or subtract? A and B. In order to add or subtract matrices, they have to be the exact same size. And again, same size means same rows, same columns. This is a different size, completely different dimension. And when you're adding or subtracting, if I asked for A plus B, how would I find my answer? Shaking the rust out, I can see it. You are just adding the corresponding pieces. And so if we're doing A plus B, first off, they're the same size. My final answer is going to be the same size, 2 rows, 3 columns. Next, I'm adding the corresponding pieces. If I'm adding matrix A and matrix B, this first piece right here is just 3 plus 8. 3 plus 8. The second piece, 0 plus 5, 5. 2 plus negative 1, 1. And so you're just going to add those corresponding pieces. However, it's not as easy as all of that sometimes. So they're going to introduce something called scalar multiplication. And so that was on the study guide. Scalar multiplication if I say find A plus 2B, scalar multiplication is kind of like a distributive property. So this 2B means we're multiplying B times 2, and everything is going to be multiplied by 2. And then A is the same as addition. So again, nothing is changing for the size at all. It's still going to be a 2-row by 3-column, but now we're going to take A plus 2B. 3 plus 2/8, 3 plus 16, 19. Next one, 0 plus 2 5s, 10. 2 plus 2 negative 1s, 0. And so the scalar, again, is like a distributive property. Everything gets multiplied by that number. And then the addition still works the same. You add the pieces that match up. Okay. Question about adding the matrices at all? Questions from the online world? I'm terrified that this thing is muted. Don't think so. See a whole bunch of red microphones, so they're muted. All right. So that is addition, and then again, if it was subtraction, you just subtract the pieces. Nothing changes. The one that he said to spend a little bit of extra time on is, matrix multiplication. So that's where we're going to end today. In order to multiply a matrix, you are going to be multiplying rows by columns, and then you get the term and add it together. So we're going to do a really simple one, and then we're going to branch into this stuff. So first and foremost, in order to multiply a matrix, the inside numbers have to be the same. We could multiply A times C because we have 2 by 3, C is a 3 by 2, inside numbers are the same, and the answer is going to be a 2 by 2 matrix. We could multiply D by A because D is a 2 by 2, A is a 2 by 3, the inside dimensions are the same, and our answer will be 2 by 3 again. Here's where it gets tricky. The order matters. We can't do A times D because A is a 2 by 3, D is a 2 by 2. That's not the same, does not exist, can't do it. And so that gets a little tricky. Just know that the inside numbers have to be the same, and that's why I had you list these dimensions up here, because it helps you to know if this answer is even possible. So, really simple. Dimensions. This is a 1 by 3. This is a 3 rows by 1 column. inside is the same, and my answer is gonna be a single dimension, 1 by 1. How we find this answer is the reason that these have to be the same number is these match up. We have 1 times -2. We have 0 times 4. We have 2 times -1. And then we just add them together. We get a -2 here. We get a 0 here. We get a -2 here. -2 plus -2 is -4 plus 0 is still -4. And so you're just multiplying the numbers that match up in the corresponding parts of first, second, third. And then the final thing is that you add them together. Really quickly, if we were to reverse this order, and I'm not gonna get the same numbers, life goes on. So, if I have a 3-column, 1, 2, 3, and, 3-row, 1-column, and 1-row, 3-column, 1, 2, 3. Now, we have 3 by 1, 1 by 3. What size is our answer gonna be? This middle cuts out. Our answer is gonna be a 3 by 3. It's huge. But, in this case, the answers are easier to come by. Because for this first row, first column, first row times first column, just 1 times 1. First row, second column. First row, second column. First row, third column. First row times third column. And so all you have to do with multiplication, if you know what size you're going to end up with, each space tells you where to get the information. This is the second row, first column, second row, first column. And so on matrix multiplication, if you know what your answer is going to be, once you set it up, it tells you where to get the information from. It's just the rows and the columns, a lot. I predict that there will be more answers or questions about which one can you multiply by, which one can you not multiply by, than actual find the product. Just because of the interest of time, they try to make the questions a little bit faster. The other one is, because it's multiple choice, they'll give you like 5 matrices. If you multiply the first 3 terms, you'll be able to say, okay, that one's out, that one's out, that one's out, because it doesn't match. And so process of eliminate as much as possible. All right. Well, they have wandered away, but by my clock we have a couple more minutes. Should I keep going?
I don't know.
All right. So, the last thing I had for you, this one is, again, stuff that they might throw at you. So, we'll do this last one and then you'll be done and I'll say, haha, I got through all my notes. If we have a matrix of x, 3, z times 6, 6, y 12 equals 18, it asks to evaluate 2x plus y plus 4z. This was the hardest one I could find in the actual review stuff. So feel free to say, I just want you to go through it with me because we're short on time, but I just wanted to show you how it can get tricky but cool. So, it's going to start with multiplication. We'll give you that hint. So, again, you're multiplying the corresponding pieces, and they're just adding together. So we have x times 6 is 6x, plus 3 times y is 3y, plus z times 12 is 12z, equals 18. And that's just the straight multiplication. The fun scalar part is, this is a 6, this is a 2. What would you need to multiply or divide by to get to 2?
Three.
Would be dividing by 3. And so if we divide everything by 3, 6x divided by 3 is 2x. 3 divided by 3 is 1y, or just y. 12 divided by 3 is 4z. 18 divided by 3, 6. And so evaluate 2x plus y plus 4z. We didn't have to find any of those values. It just equals 6. So, even if you have no clue how to get to that, by just multiplying it out, you got really super close, and it was just a scalar, just a distributive property. You can divide the whole equation by the same thing, and it gets you to what you want. So, that was the trickiest problem I could find for matrices in the whole thing, but it is there. And with that, we are out of time, so thank you so much.